Hello, welcome to the second live session of Points of Topology Part 2 NPTEL course. This is Shovik, working from Kasilingam at Madras. And this is a 2-week course, and this is the second live session for this course. Okay, so before starting further, so it's Mustaq. Okay, Mustaq, can you please confirm whether I'm audible and is the screen visible to you or not? Can you please confirm? Mustaq Ahmed, can you please confirm whether I'm audible and is the screen visible to you or not? It seems there is some internet issue. Uh, Mustaq, can you please confirm whether am I audible and is the screen visible to you or not? Hmm. Hmm. Hello, am I audible and the screen is the screen visible to you or not? Can you please confirm? Okay, so it seems I'm audible and the screen is visible to you. So let's start. So it is the live session 2. So before starting the today's session, let me know, do you have any question or doubt? Before starting today's session, let me know, do you have any question or any doubt? Please don't hesitate. If you have any doubt or any question, please ask me. Okay, so in case if you have any doubt, um, please unmute yourself and let me know. Okay, so okay, so last day we have done the separation axiom things. We have done the basic separation axioms. Okay, so sorry, last class we have done basic. Last class we have done the basic separation axioms. Okay. Yeah, there are many things left till now. We shall get back. We shall get back to the advanced things. We shall come back to advanced things soon. For the time being, we shall not focus on countability axioms. Okay. So the countable axiom start with there are two things the countable axiom. First is first countable axiom, first countability axiom, and second one is second countable axiom. Okay. So we shall start with the first countable axiom. Okay. So the definition goes as follows. So let X be a space and let X belongs to X. Then capital X is said to have countable basis at X if there exists a countable collection beta of neighborhoods of X such that each neighborhood of X contains at least one of the elements of beta. And a space that has a countable basis for all X belongs to X, then X is said to be first countable. So that is the definition. So this definition show so first countability axiom is that suppose X base space, okay? Suppose the X base space, and then X is said to be have countable basis at X at some point. E there is a countable collection beta of what? Of neighborhoods of X such that each contains at least one of the elements of beta. There is space, then it's said to be countable basis at X, and a space which have a countable basis for all X belongs to is called a first countable space. Okay, so that is the definition of first countable space. Okay, so till now is this definition clear? Please let me know. I shall be back within a few minutes. So till now, is there any confusion and problem in the definition? If not, then we may proceed for the next definition called the second countable axioms. So for the second countable space, the second countable axiom, let me write it down. Second, the second countable axiom. A space, a space X is said to be second countable if it has a countable basis for its topology. Space with second countable if it has a countable basis for its topology. Okay, that means what? Hmm. That means there exists a collection beta such that for any open set U and for any point X containing U, there exists B belongs to beta such that X belongs to B subset of U. This is what by we mean the it has a countable basis for its topology, and of course this is countable set. Beta is a countable set. Okay, so that is called the second countable space. Okay. Now, okay, so let me know till now. So till now, the first countability and second countable definition I've given. So please let me know, do you have any question or any query regarding the definitions? Please let me know. Take your time. So if any question or doubt, please let me know, or else we shall go forward for the application of first countable and second countable axioms. Okay, so it seems till now there is no doubt, no for question. So let's move on up to next theorem, which states that why the countable axioms are so important. Okay, so first theorem. So see, we have seen that for any metric space, for any matrix, if it's continuous, if and only if it's sequentially continuous, right? But the same is true not the topological spaces. That is, in any topological spaces, if a map is sequentially continuous, that doesn't guarantee that the function, that original function is actually continuous, right? But in case of a first countable space, a sequential continuity is enough to ensure that this function is continuous. So let me write down the statement clearly. Let X be a first countable space. The function f x to y is continuous if and only if for every convergent sequence x in x converging to x, the sequence f of then converges to fx. So the statement is that, if the domain is a first countable space, then then the usual continuity is same as the sequential continuity. Okay, that is the thing. And second theorem is that, so in general, you know that, oh, that's always a statement. So please take your time. So proof. Try yourself first. So try this proof first. Try it first. Take your time. Okay. So, Mustaq, are you able to solve it? Mustaq, are you able to figure this out, how to approach this problem? Any idea? Or can you please suggest some way to solve this? So for this, so there is a hint. First, try to solve the hint by yourself. Okay. See, in metric space, we know what. Suppose A is a closed subset of capital of a metric space X, then X is a closure if and only if there is a sequence X in an S, other Xn belongs to A closure. Okay. But the converse is not true in topological spaces. But on the first countable space, this is true. So the statement is that so X belongs to A closure if and only there exists a sequence of points in A converges to X. So this is the hint of this problem. So using the fact this is first control, try to solve the hint by yourself. Okay, take your time. Okay, Mustaq, are you able to sort out this hint, or at least can I give some idea how to approach this one? Okay, so let me do it by let me do it. Okay, so so what we need to figure out? We need to figure out, suppose there is sequence X in A converter. So it is given the X belongs to A closure. Okay, that implies if U be an open set containing X, this implies U intersection A non-empty. Okay, now being first counter, there exists a countable basis at X. Call it beta. Okay. So this countable basis, we are writing this, denoting this as u1, u2, un. Okay. Now say x belongs to a closure. This implies what? There exists x1 belongs to u1 intersection u. There the u1 belongs to u1 subset of x. Okay. Now we are putting v1 to be u1 and v2 to be v1 intersection u2 dot of vn. There is u1 intersection vn minus 1. This collection v1, v2, vn. This collection forms a countable basis of x. So clearly by construction, v1 contains v2 contains vn contains dot dot dot. Okay. Now choose xi belongs to vi. Okay. For all I. The claim is the sequence xn converges to x. Okay. Now please try yourself with the sequence x converges to x. How to do it? Okay, take your time, let me know. Okay, Mustak, are you can you please unmute yourself? Let me know how to show that x converges to x. Do you have an idea? Any idea or can you tell? Do you have any suggestion regarding how to solve this? Okay, so the proof of claim. So take any open set U. Take any open set U containing x. Okay. Now since V1, V2, Vn, dot this forms a counter, this is a countable basis at x. So there exists n such that x belongs to Vn subset of U. So this implies what xi belongs to Vn subset of U for all I greater than equal to n since Vn contains Vn plus 1 contains dot dot dot. So this tells us the sequence xn converges to x. That means what? That means if I take that means so we are done. That's what so that is the one direction we want to show. So what is the question? The question was that let x be a closure. So there is a sequence of point of a converges to x if and only if x is a closure. So one side is obvious. We need to show what? We need to say if x goes to a closure, there is a sequence of points x and in a which converges to x. So that's what done. Okay. Now using this, try to solve the original problem. Hmm. Using this, try to solve the original problem. That is what you need to start. You need to start. Suppose if it's a function, so that for any sequence x in x, convergent to x, f of x and converges to f of x. Now show that f is continuous. Okay. Take your time, think about it. Let me know. I still have 5 minutes. So using the heat, anybody will to solve the main problem? Using the heat, is anybody able to solve the main problem? Let me know. Okay. So, the main solution. So it's given for any sequence x in f of x equals to f. Okay. So to show what we show, suppose a is subset of x, then f of a equals subset of f of a whole closure. Is this thing valid or not? If they satisfy, then function will continue, otherwise not. Right? So what to do? So what to do? So we need to set theoretical proof. Suppose take y belongs to f of a closure. Okay. This implies that y is equal to f of x where x belongs to a closure. Okay. Now by hint, now by the hint, there exists a sequence xn in a and xn converts into x. Okay. By property of f, by property of f of xn goes to f of x. And note that f of xn, this sequence is in a f of n f of x equal to y. This implies y belongs to f of a whole closure. So this tells that f of a closure is subset of f of a whole closure. Okay. Please let me know are you able to understand this or not. I said back a few minutes. Okay, so let me explain. I hope this argument is clear to you, but still let me explain, okay? Because I don't think the technique is known to you, okay? So what is the theorem? The statement states that if a space first question is why one should be interested in the first countable, second countable thing at first place? The answer is in this theorem. So in matrices, what we have seen in matrix, we have seen that in the usual continuity and sequential continuity are same, correct? Also in matrix, we have seen that if A is also of X, then X belongs to A closure if and only if there are sequence X and A converging to X, okay? But in general, these things are not true in a topological space, okay? So that's why if we assume this is the first countable, then those things comes to be true. So that means what? If a space is first countable, it is likely, it is somehow quite nearer to the metric space. Okay. So moreover, suppose if I say second countable, it is more about to be a metric. It is not metric space, but it is going to be a metric space. Okay. Then if it satisfies all separation axioms, then one can say that it's almost closer to the metric space. Okay. And then under certain conditions, the spaces will be, there exists a metric under certain conditions. Okay. So basically, these properties, first countable, second countable axioms, separation axioms, these properties are telling that's what is the probability of the space to become a metric space in some sense, in some sense how much it is nearer from being a metric space. You can think like that, okay? Of course in mathematical. So okay, so now let's go to mathematics here. So the statement of theorem tells that suppose x the first quantum space and f x to y the continuous if and only if for every convergent sequence x in x convergent to x, the sequence f of x converges to fx. Okay, so this is the statement. So in order to prove that, first we have proved that suppose x is a sequence xn in a closure if and only if there is a sequence xn in A such that xn converges to A. So this is the convert statement in general we have seen the metric space, right? So this particular thing we first now want to prove. Okay, then using that we shall prove the main thing. Okay, so let me know till now is everything clear or not? Please let me know. Okay. So now how to show to prove this? So we need to actually prove the converse, right? So I mean, of course, if x in a sequence of points in A converges to x, then of course x in A, there is nothing to do that. We need to converse. So suppose we choose what? So we choose x belongs to 1 minute. So we choose x belongs to A closure. Okay, that means what? If we choose an open set containing this is an open U is an open set, then U intersection A is not. Okay. Now, since X is the first countable space, so there is a countable basis at X, call it beta. And suppose this countable basis contains element U1, U2, UN. Okay. Now to the C. Here we have some arbitrary U1s, U2, UNs. Okay. Now what are we doing? We are making this thing to be bigger to smaller. So V1 is bigger, then V2, then V3. In that way, we are creating. Okay. So V1 is equal to U1, V2 is equal to U1 intersection U2, which is subset of V1, Vn inter U1 is UN intersection Vn minus, which is subset of Vn minus 1. So it tells that what V1 contains V2 contains Vn minus 1 and dot dot dot. So this forms a countable basis of X, okay? And by construction, this thing hold, this property hold. Now, for each from each vi choose a xi. Okay, now claim is that sequence xn converges to x. Okay, so how to do that? So choose an u containing x. Since this v1 will counter base of x, there is as the x of vn subset of u. Now by definition, now since vn's are decreasing, so since one vn if inside u, then all the vn with indexes are bigger than capital N, those vn's shall lie inside u, within u. So vn is so that's what the xi belongs to u for all greater than n. So the xn goes to x. So that is done. Is the argument clear to everybody? Is the argument clear to everybody? Please let me know. Let me drink a glass of water. So now, suppose A subset of X, okay? Now we need to show that f is continuous. So for that, we need to show that for any subset of X, f of X, if of this holds true or false, that's what we need to check, right? So we choose y belongs to f of a closure. So that means y is fx for some x belongs to a closure. Then by the hint, what we got? So by the hint, we got that their sequence xn and a, so the xn goes to f. So by the hypothesis of f, that tells that f of xn goes to f of x. This of x or y. So this tells that y belongs to f of a closure. By the previous hint, this tells if of a closure subset of a whole closure. So this tells that f is continuous. Okay. So is this argument clear? Okay. So if this is clear, then we can go for the next thing. Is this argument clear? Please let me know.
Yes, yes.
Okay. And also, if you have any question in between, please unmute yourself and ask. Okay, there is no need to hesitation. Okay. So now we have seen the definition of second order analysis. Okay. Now, there are two things. So there are two definition now introduced. One is Lindelofness, and second is separability. Okay. So Lindelofness tells that by Lindelof we mean that every open cover has countable subcore. But separability means that it has countable dense subset. Okay. Now, there are two properties which tells that second countable implies length enough and say whatever. Okay. So the proof we shall see the proof later. That the proof is not important right now. So RL, try to show that RL is not second countable. Well, there is no point of using any kind of properties in the separability because R with lower limit topology is Lindelof as well as separable. Show that R with lower limit topology is not second countable. Okay, take your time and let me know. Mustak, are you able to figure out why R to low limit topology is not self countable? Do you have any idea it is how to start with? No need to hesitate. If you have any idea, please let us know. So, so let R with low limit topology is self countable. So R with second countable. So and now choose x, and we have the open set x comma x plus one, right? Since our second countable, so call beta b its countable basis. So this implies there exists beta x belongs to beta such that x belongs to beta x subset of x comma x plus 1 by n. So this implies infimum of beta x is equal to x. Now, so this tells what? This tells if x not equal to y, then implies beta x not equal to beta y. This implies the collection of beta x is not countable. So this implies R's dual limit topology is not same countable. Okay, so that is the argument. So Mustaq, let me know. Are you able to understand this argument? Take your time. Let me know. So is the argument clear that which states that why R with lower limit topology is uncountable? Is it, I hope it is clear. So now, sorry, it's not uncountable. Okay, but the standard fact. Okay, so we have seen that. So, but there is a standard fact which will prove later. The fact is R with lower limit topology is Lindelof. Proof difficult, hence we shall do it later. But RL is separable. Why? Because Q is dense in R. Okay. So notice that RL is Lindelof plus separable, but not second countable. Okay. So there are some theorems. Let me state these theorems at least. So there is a fact which tells that for a metrizable space, separable or Lindelofness implies second countability. Second, for a matrix space, if it is either separable or Lindelof, then it is second order. But you've seen the R lower limit topology is Lindelof separable but not second countable. So that tells that. So hence R with lower limit topology is not metrizable. So that is the thing. Okay. So till now, is it clear to you, Mustaq? Let me know. Please take your time and let me know. Okay. Okay. So, so I hope this one is clear. Now let's find the next problem. Let me find. Hold a moment, please. Hmm. Okay. Now, so in the countable axioms, now we shall discuss about the effect of taking the product, whether the same angiome is getting satisfied or not. That's what we are now interested to understand. Okay. Okay. So now, I'm writing the statements down here. I'm not going to the proof is not that important. Okay. I mean, sorry, the proof is important, but those proofs are quite easy, so there is no point of writing down those proofs. Okay. The fact or theorem or statement, what you say, that's okay, but that's not the problem. The problem point is that countable product of the first countable space is again first countable. Okay. Countable product of second countable space is But, 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 product of lingular face space need not be lingular. Okay. So, okay. So first of all, product of first count, the product of counter product of first counter second counter space is first or second counter. But the convenes yours to the restroom. I'm not going to prove that. So what I'm going to prove is that I'm now going to exhibit an example which shows the product of linear space not necessarily enough. Okay. So 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 it is known that RL is linear. Okay. It is anyway known as surgeon Freiline. Okay. Claim is RL cross RL, that is RL. It is known as surgeon Freplin. It is not linear. So So for that, what we need to do that we need to exhibit open curve which does not have the counters of curve, right? So we are also consider the line x minus x belongs to RL. Okay, and consider the open set here. So that is what each. Okay, so first each point of L is open in L. Okay, to the first observation. Second observation, A is a closed subspace of R. Why? Figure this out. Okay. Now, so RL2 can be written as RL2 minus L. This is one set union. Singlet X belongs to L. Okay. So each of these is open. Okay. So now if this RL is Lindelof, then it must admit counters of cover. So this implies what? This collection must admit countable subcover. But that is not possible since line is uncountable. So it cannot be covered by counting remaining points. So that is the argument. Is this clear? Please let me know. So let me explain. So basically, what we're trying to show is to show that. So see, counter product first countable is first countable, and counter product second countable is second countable. But the same thing does not hold in case of linear levels. That is the product of two linear levels is not linear level. So forget about countable product. Okay. So for it, I am going to construct an example which tells that product of linear levels is not nice linear level. Okay. Hmm. RL is linear level. So RL plus RL is certain free, not linear level. So we're going to show the RL cross RL is not linear level. Okay. So for that, we are considering the line x comma minus x. Okay. First of all, observe that each single point is an open set in the line. So under the surface topology, the line has a under the surface topology of the line is nothing but discrete one. Okay. So now L is a closed subset. Just figure it is a while L is a closed subset. Now we are taking R of L2 that is equal to R L2 minus L union those single points. Now, if RL is linear, then that open cover must be countable subcover. But that singleton X exists, well, this thing cannot admit a countable subset. Why? Because L is uncountable, and so it cannot be covered by its countable thing. So that is the R of L2 that searchable place is not first countable, is not Lindelof. Okay, so that is the argument. So is the argument clear to everybody? If yes, then then let's move on the next question, namely, okay. So try to show that. So we show that Quran Lindelof is not Lindelof. Okay, but if one is Lindelof and another one is compact, this implies X cross Y Lindelof. Question is why? So basically, see, for that you need to proceed along the definition. Sorry, proceed along with the definitions. Hint is proceed along with the definition. Okay. Okay, so take your time, think about it. How you can show that X was in the lab. Okay, just you start with an open cover and try to use the compactness somehow. Basically, it is same as the the proof of tube lemma that we have seen in the previous semester. So the proof is almost same like that. Please take your time, think about it, let me know. So, so, so what we'll do? So start with the open cover. Let U alpha be an open cover. Okay. Now we somehow use Lindy roughness and compactness. So the hint is use the techniques of tubular neighborhood. Use same technique as of tubular neighborhood theorem. So yeah, so that's what you need to do. Okay. So 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 yeah, you can do it by yourself in your home because this particular thing shall take few moment time and there is no and this proof is actually nothing new. We are not going to learn anything new. Okay. So Pustak, let me know. Do you have any question or any query? Okay, it seems there is no question, there is no query. So for today, let's end here. We shall meet on the next Friday, same time, 2 hour session. If you have any doubt, any question, please ask me in the next session. Okay, I'm ending the session. Thank you.